Okay, so this is the first physical lecture for me for a couple of years. I made an announcement last night at some point about the way that the course will be delivered. Basically, we're going to try and make it as flexible as possible on your side. So we made all video lectures and an online assignment last year. I see no reason for any of that to go away. We'll just add to it for this year. So all of the video lectures that we did last year are already available online. You can look at them whenever you like. Go ahead if you like, but no requirement. The lectures I'll give here will be ballpark the same. So I don't follow a script or anything. So stuff in the lectures right now will be, updated for specific things that are going on this year, and maybe I say a little different things. But for me, you can use it how you like. So you can come into every lecture and every lab. That's great and encouraged. You can equally look at the lectures at home, do your labs at home. What I would say is reflect as you go on, kind of what you need from the course to do well. So obviously, if you try the online lectures and it doesn't work so well for you, or you have a lot of questions, you need more support, then probably you should come in. And vice versa. There'll be some people here who maybe have done a lot of embedded programming before, maybe used a real-time operating system, I don't know. In those cases, then you might fly through the material and decide that you can manage with the online version. All absolutely the same for us. So just find your own path and see what works.
I have a small question about the announcements.
Yeah.
Are you supposed to get emails when you do announcements like these?
Yes, you should do. Did you not?
And I think there's probably other people as well, because we were like 15 or 20 here at 8:30.
Oh, interesting. So of those, can you put your hand up if you did see an announcement? Okay, so it's some significant block of students, probably in a certain course. Do you know what the common denominator is for you guys?
No idea.
Okay. Give me 1 sec here. Let me just double check that you're enrolled in the normal. Anybody who's enrolled, every TA even, they all get the same announcement. So let me just double check, if you don't mind, that you're in here. Oh, that's a good start. No, I logged in last night. This is fine. Would you mind if you give me your number?
Valentin?
I think it will search on... This is you?
Yeah.
You should get the announcements. So beyond checking you're in the course, I don't have any extra insight into behind the scenes stuff. But if you don't get announcements, it's definitely something to check because, lots of stuff can happen. We might be announcing grade releases or some tip for the labs or whatever. So sorry, I can't help too much more, but you should follow it up with the Toledo people.
Thanks.
No worries. Taking a look at the schedule first, then we'll jump into the real introduction. I'd just like to give you an overview of the broad strokes of what we're going to do and how we're going to do it. Everything happens in this room or online, and it's always the same time, same place every week. So it doesn't matter if it's a lab or it's the lectures. You come here, or again, do it online, either way. We're going to begin with a block of lectures, which is hopefully sufficient to give you the basics to begin embedded programming. Now, it's not a programming course, so the lectures won't be super focused on the syntax of how you're going to express your programs first in the Arduino IDE and then later in FreeRTOS. It's not going to be like that. But there are important concepts underneath that you still need to know before you even get to the code. So we'll begin by really going kind of brick by brick. We'll look at computation, memory, and then programming support. Then we will get into embedded I/O and concepts of time. The course is not large enough to kind of make anybody embedded experts or anything like this, obviously. I have kind of two ambitions for the course and what it can give you in a relatively short, time. Number one, it can kind of demystify a lot of what embedded programming and real-time development is, so it is not in any way scary or strange to you. And also give you the kind of enough of a taster that you find out if you like it, if this is an area you want to work in, and give you just about enough expertise to confidently say you can begin working in the area if you go to a company. There will not be enough expertise to, kind of go and knock out like super energy optimal real-time code. But I think we can kind of give you an experience of most parts of that process and kind of like, make it, what's the word? Take away the scary elements of all of that kind of stuff. We will do the labs in 2 blocks. This is part strategic, but also part pragmatic, to be honest with you, because we have some blocking things for me and Yolanda in these areas. The first block will really be getting to grips with an embedded device, some test equipment too. So power, for example, is going to be a big part of what we do in this course. And so you need something to test the power consumption of your device. So you'll all be getting a fairly capable multimeter, a couple of little embedded boards, and beginning to program them. We aim to start really easy. So it's not, how to put it, a lot of courses will like to go really foundational bottom up. So if you want to know about embedded programming, you should first know about assembler. This is definitely a good thing to know, but that's not what we're doing here. We're going like the easiest possible funnel down. So you're going to start working in the Arduino IDE, kind of writing simple C++ programs that are going to be not terribly more complex than Hello World Java programs. But step by step, things will be added. So you will then be expected to deal with real embedded I/O, which is much more, much less abstracted than what you would see on a mainstream machine. You actually have to understand what's going on there. Things like interrupts, time, and so on, but still in this nice kind of protected Arduino C++ space, where you can find a kabillion examples online that people have done for you. Then we jump back into the lectures for a couple of weeks, and here we start touching the operating system and real-time part of the course before returning you to the labs. Now, luckily, there's a very nice, shallow path between Arduino-type programming and real-time programming through the FreeRTOS libraries. So we'll get much more into what FreeRTOS is, but it's not an OS like Windows or Linux or anything like this, or even Android or, let's say, Raspberry Pi Linux. It is really just a set of libraries, coding conventions, semantic support that you can bolt into other programming environments. So you can run FreeRTOS, if you were so inclined, within a Linux shell to give you real-time scheduling. Here we run it in the Arduino IDE, which is a standard way of running it, but you still get to use all of the same concepts. Things like semaphores, introducing your own tasks, real-time interrupts, and also immutable schedules and stuff. So you get all that experience, but you don't have to go and use any very exotic or different programming language. Every year, we also have some more experienced people who would like to do that, who would like to throw away the Arduino IDE and do everything in C, or start bolting in little bits of assembler to do stuff more optimally. That's awesome if you can do it. Encouraged, and we'll help as much as we can. But it is not required. So you can kind of stay reasonably high level, I think, at least, throughout the whole course. But you're absolutely welcome, and we'll provide as much support as we can if you want to jump in deeper, if you want to kind of dig under the hood, really play with registers directly, replace some suboptimal I264 code with your own version, whatever you want to do. We will mark the assignments in we will have code submission. We'll also have demos and testing. So much more details will come later, but this is kind of an interactive session where you will drop in pairs again this year. Last year, for the first time, it was singles due to COVID and people working at home. But you'll have your team, you'll work in a pair, you'll go and do a demonstration, You'll be asked to explain your code. This is kind of normal, kind of like the Java exercise of computer networks. But now you'll also have some, quantitative tests. So your power numbers will be measured as you do this and things like this. I think it's one of the I hope one of the more fun bits of the assignment is it's really all about performance, actually. So you'll have to hit some timing requirements and some power requirements. And how you do that is very open. We'll be running the same assignment as last year. We know what the best people have done so far is, but it's always possible to do better. So if you think of some kind of cool or weird way to do this, and you make your power numbers better, fantastic. You do better in the assignment. It isn't that there is one right way to do it, and if you do it wrong, then you get a lower grade. Whatever works for you to get the lowest power consumption, the most timely responses in your code, is the best code in this class. So I think that is as far as I will go on the schedule. Any questions overall? Nope, everyone seems to get what's going on. This is good. Then I will start with the introduction. Yeah, so I think I talked about all of this. We think it's going to be kind of an equivalent experience online, but not guaranteed. So you need to keep an eye on that and see if you need more support. And if you do, then you should come into class, come into the lab sessions in person as well. There'll be little kind of milestones as you go with the labs, for example. So it's not just the assignments at the end. There are some home exercises and stuff. There's things you're expected to do week by week. So you'll know if you're hitting those targets or not. So I kind of mentioned this already, but the philosophy behind this course is to try and bridge what we see as this emerging gap between the skills that are needed in industry and the skills that people typically graduate with from computer science courses at places like KU Leuven. It's a very interesting space for me because it isn't that we want to make you into electrical engineering students, that if you just know a little bit more low-level C, for example, then you can operate well in this space. More and more what we're seeing is things like machine learning being tied to embedded sensors, monitoring acoustic signals, vibration signals, who knows? Everything about people, everything about machines. And these are connected to real large-scale distributed systems. So what's needed are people who can kind of straddle that very wide space. On the one hand, not be scared of an embedded sensor and how it should connect to an IP-based distributed system. On the other hand, be able to architect large-scale systems to build things in a way that's scalable as well. And you almost never get those two things together in the same person. It isn't that you have to be an expert in all of that, but even to have some knowledge of all of that, I think is extremely rare in, if you look at these kind of industrial posts. But it's exactly what's needed. Typically, we have people working kind of in different stovepipes, basically. Fantastic embedded engineers who don't give a crap about networks, distributed systems, or the back end. So they build completely efficient code on extremely efficient platforms that is not fit for purpose because you can't integrate it with shit. And then on the other side, you have high-level software engineers who just want the data and consider all of this, every single thing you'll learn in the course, complete ephemera that somebody should do for free, and it should just exist. And neither of those things are reasonable, and neither of those things happen in the real world. A lot of the hype behind the huge-scale IoT systems hides this huge yawning chasm that's really difficult to bridge, in fact. So yeah, what we hope you're going to get is a theoretical foundation in embedded and real-time systems. There's a lot of focus here on embedded as well, so understanding and being basically competent in power management, in using the, how to put it, the kind of the widespread commonplace embedded IOs that we have, understanding how to deal with embedded memory, things like this. And also learn best practices in embedded software engineering. generally speaking, and definitely applies to your assignment, whenever you're working in this space, we end up with this kind of iterative cycle of modeling, design, and analysis. While iterative kind of short development cycles are encouraged everywhere these days, it's especially important in this space because quite often we'll be building something to study the physical world. So until you build it, until you get it in place, you actually don't know everything about the problem. It's impossible. You haven't observed it yet. You're building a device or you're building a software stack for a device to observe the physical world in the first place. Once you have observed it, then you can refine your design, perform some analysis, and you cycle right back again. So it's an area which is intimately tied to observation of the physical world and adjustment. And that will serve you very well in your assignment. So, you know, if you try, for example, to go all the way to the end before doing your timings and your power measurements, and you think you have architected this beautiful best practice system in FreeRTOS, 9 out of 10, it won't work, it won't go into low power mode, and the timings will be awful. Very simple, but these short design cycles will serve you very well. Digging into each one, if we talk about modeling, here we're not only talking about the what's inside our software. Normally, the modeling that we teach you in computer science is about the internals of the thing you're building. That's very important here, but so too is the physical world, because these things connect to it. So whether it's a machine, the physical environment, it's the person that, like a heart rate sensor, for example, will monitor, you have to have, at some high semantic level at least, a model of what that thing is and how you expect it to operate, as well as a model of the software and the device. Obviously, we all know what design is. We then start to realize a software system that working on top of the model accomplishes our aims. And then we need to analyze that. So here, we have the same kind of factors you always care about in software. How big is it? How fast is it? Are the answers correct or not correct? But in addition, we have these other factors. So we have things like power consumption that are really important. And in the case of real time, we also really emphasize the how fast is it part. So I'll come back to this. But real-time systems are not about going fast. They're about providing an answer on a fixed timeline. There's tons of places in the physical world where if you don't do that, the system cannot work. It doesn't matter if you're eventually correct. If your whole job was to activate a pacemaker, right, when somebody has a heart attack, you'll write a week later, it's still wrong. So there's a supporting book that goes with the course. It's provided online in PDF format. This isn't pirated. It's OK to download the book in PDF, although it can't be printed. Just like the online versus physical aspect of the course, I leave it up to you whether or not you want to buy the book. We probably use somewhere between 30 to 50% of the material in the book, so that might make a difference to your purchasing decision. I would say the best thing about it is it will explain things differently than I do. So you'll get the lectures, there are obviously the slides, and then there's different people to help you in the labs. If at the end of that, you know, you don't have a clear view on a specific topic, you'll almost certainly have that resolved by the book. I would perhaps start with the PDF copy. If you either really enjoy it or you find you really need it, then you can go and buy the book. In terms of the breakdown of marks for the course, we follow the ECTS specification. So that allocates 2.7 credits for the lectures. That's assessed on a written exam in January. It's a very simple exam. It's a closed book exam. I forget how long it is right now, but we always do 1 hour less than the official slot to accommodate extra time. And you have a number of short questions. They're not engineering questions. We evaluate all of that in the assignment. It really is a test of your knowledge. So do you understand embedded memory, programming conventions, how the scheduler works, embedded buses, power management basics, stuff like this. So short, relatively closed world questions. The 1.3 ECTS credits is all about that assignment. So as you can see, it's a large part of the course, and that's why it also gets so much time out of our schedule. I guess another thing to emphasize as well is they do reinforce each other a good bit. So there'll be lectures on memory types. And of course, if you remember the lecture on memory types perfectly, you get 100% on the exam question. But you'll also be working with those memory types in the assignment. So, you know, it'll be so much easier to remember which ones are which and what they do and why they exist if you do a good job in the assignment and if you use them right. Okay, so any questions so far on the division of the course or the way the assignment works? No? Then let's talk about one of our 2 core terms in this course. That's cyber-physical systems. So cyber-physical systems are systems where what we're building is part of the physical world. I guess you can say everything is, right? So your software lives on a server in a data center somewhere. It doesn't literally float in the ether. But here, the difference is we have to care about that physical world. Not just that we have enough resources to run and so on, but we have to understand and model the buildings, machines, robots, other bits of infrastructure we might be embedded in. And I should have included people there, by the way, as well. There's a huge, it's hard to say exactly how much, but a large part of the cyber-physical system marketplace is devoted to things like personal health and telehealth and things like this. So quite often, you know, yes, it might be a machine, but it can equally be a person who's the system we're interested in. So that part is physical. And then on the other hand, we have our digital part. And that's our control software, visualization, logging, all of that good stuff. This union of the two, right? So that the fact that the digital is connected to the physical makes this a very interesting area right now. I'll have some application examples shortly, but the idea driving the cyber-physical systems domain is if we can increasingly digitize all the things around us, ourselves, but also the buildings, the machines, et cetera, then we can remove a ton of manual effort from the world. We can connect those things to either simple control systems running globally or nationally across different regions, or on the other hand, to machine learning, as I mentioned previously. So we can have the computers start to take care of our physical environment just as well as they do our digital environment. Typically, the application areas, although there are many different ones, are really all about efficiency. That's these first 2 points. So studying how infrastructure is used in order to eliminate wasted energy, for example, is a classic, but also in order to eliminate wasted raw materials. Because, for example, you don't know how fast your production line is really running, so you ship in more material than you need, and at the end of, I don't know, a build run, it goes to waste. Things like this. Increasing quality is also related there. So, for example, one of our spin-offs, VersaSense, is working in an application case where they study the sounds that are made by electric toothbrushes after they're manufactured. Doesn't sound so exciting, but it's actually a tricky problem because when, gosh, I've forgotten the name, P&G makes those things, like they either work or don't work. They make hundreds of thousands every day. They're very, very cheap. So you cannot have a person go inspect every toothbrush. That would be ridiculous. The person would cost you far more than the broken toothbrushes will. But an array of microphones connected to a real-time monitoring system can study the sounds they make when they're turned on. If they're good, then they proceed. If they're bad, in real time, they get kicked from the production line before going any further. So it's a silly little example, but it's a good example of how like a cyber-physical system can increase quality. But note again, it's always tied to reducing waste as well. So that's the first definition. We have cyber-physical systems, CPS. Our next definition concerns embedded systems in general. So I think when people use the word embedded systems, we can mean a lot of different things. Technically speaking, and I do think this is correct, an embedded system is just one that is connected irrevocably to a particular application context. So if you think about something like the internet, it is not an embedded system because it serves many different applications. It reaches into homes, it runs in the internet core, on non-standard processes, etc. An embedded control system, on the other hand, is tied to and typically optimized for the machine it monitors, the body it monitors, its specific task, and it's optimized like that. You cannot take, typically, a real embedded system and then use it for general purposes. That would be a strange and crazy thing to do. You might be able to get it to work, but it's not designed for that at all. Another element of embedded systems that comes from that fixed integration is that we see a much higher degree of monolithic integration. So whereas your mainstream laptop or your desktop or a server strive to separate functionality into reusable blocks, your graphics card and its GPUs, your processor, your memory, and so on, here, to minimize costs, we typically integrate everything together. And that has a dramatic effect on how cheap these things can be. Because in the end, of course, you put all of your investment in electrical engineering into designs and to running the first prototype. The nth prototype is just a question of more silicon. In the end, it's a question of more sand. So everything else stays expensive. Adding extra chips to a PCB has some kind of extra time associated with it, extra manual effort. In the end, once a chip like this is ready with all of its goodies embedded on it, costs can fall to almost arbitrary levels depending on scale. You can buy a micro today on DigiKey, which would fit on a pinhead and is more powerful than the computers that I've used for years when I first started my computer science degree. So what are those peripherals likely to be that you don't find embedded on your mainstream processors? Things like analog to digital converters. Don't worry, these acronyms will be explained later. Digital to analog converters, pulse width modulation, different kinds of accelerators for analysis, things like fast Fourier transforms for signal analysis, fast Hartley transform, cryptographic blocks for doing fast encryption of your network traffic, things like this. It's not necessarily that you wouldn't find any of these on a central processing unit, but they'd be relatively rare. We tend to separate here because we're less concerned about cost than, for example, performance and flexibility. Here we give up flexibility and we're just optimizing for performance and cost. Now, one thing that's kind of weird, though, is when a lot of people talk about embedded systems, they're not talking about any of that, right? So you might think about embedded systems like, for example, an Arduino. Easily the most popular way, at least in Europe, to get started with embedded systems. Now, is that really an embedded system like I just talked about? I would say not really. There's not much on the core Arduino board. I'm just going to talk about one version of Arduino, the Arduino Uno, a standard like 8-bit Arduino here. You have a processor with, yes, an ADC and interconnects and stuff, but it's even designed to have plug-in boards, very much like a motherboard, right? So you can plug in a fingerprint scanner or a microphone or whatever it is you want to plug in. So on the one hand, it is built using these embedded processors, which are small, highly integrated, low cost. But increasingly, whether it's the Arduino or the Raspberry Pi or our spin-off VersaSense's product, we're extending these with more and more like plug-and-play modules. So on the one hand, you have true embedded systems, and on the other hand, you have these kind of resource-constrained embedded systems where people are doing interesting things, but not in a specific application context. You cannot say the Arduino is embedded for any specific app. It doesn't make any sense. That takes us to our third definition. I think it's the final definition for now, and that is real-time systems. So typically, if you're talking about the correctness of a program that you write in a formal sense, all that you're talking about is that your program gives the right answer. You might also talk about performance of that program. How fast is it, big is it, and so on. How much memory does it use and whatnot. But fundamentally, it's correct if it gives the right answer. In a real-time system, that's not true. Correctness depends on giving the right answer and within a well-known deadline. It's very, very common to think that real-time means fast. Just like embedded is a synonym for slow processors, real-time is a synonym for running really fast. It's not at all. You could have an extremely slow micro controlling a system at a very low rate on a very tiny power budget. It's still a real-time system. But what matters is it's engineered in such a way that it provides the correct answer on a definitive timeline. This comes up in so much embedded design, even if you don't think you're building a real-time system. So, for example, if you use an accelerometer with a buffer, it takes a certain amount of time to fill. And imagine you want to do step counting. You're going to look at the buffer and you're going to count the steps that someone is making. Well, better make sure that the calculations you do on that accelerometer data are done by the time the buffer fills. Otherwise, you could miss a step. So it isn't, in my opinion, that real-time systems are this kind of separable niche either. Basically, most interesting, useful embedded systems are some kind of real-time system. There's very few that really operate tied to the physical world and don't have any deadlines. That's actually pretty rare, in fact, I would say. Within the field of real-time systems, we have two broad classes. We have soft real-time, and in that case, we have some deadlines that can be missed and some that cannot. And we have hard real-time, where no deadlines can be missed. The more complicated a system gets, the more you're likely to have layers of priorities and layers of trade-offs about what should happen when, and in which cases different deadlines could be missed. As a really simple example, if you imagine a production line with an emergency stop functionality, once you're in the process of doing emergency stop, there's a whole bunch of functionality which might be real-time normally, but can now be dropped, because the whole point is to shut down the line. You don't care anymore about counting, perhaps. You don't care anymore about monitoring vibration in the motors, because you just turn them off. This leads us to rather complex schedules compared to what you might be used to in your other courses. And again, because we're focused here on, what's the word? The real fundamental notion of time, it's even different than if you learn threading, for example, and you're doing like a nice, efficient kind of program with multiple threads. Here you have the same concerns, but also you have to think, again, all the time about the real world and real time. There are a bunch of examples in the book. I do think it's interesting to read the PDF and take a look that talk about what real-time and embedded systems look like. So here's an example. I'll just talk through it really quickly and why it's a little bit interesting to us. So here you can see that we have two separate platforms. These are the highest level blocks, and they're tied to something here called a physical plant. This is the real world. It could be a body, it could be a machine, we don't care. The fact that we have two platforms here is really, really common and increasingly common these days. What a platform is may not be immediately obvious. So yes, it could be your Arduino board, and the network fabric is I²C, and your plug-in board for the Arduino is the second platform that also has a compute module on it and is doing something clever. At the same time, this network fabric here could be an industrial bus connecting sensors across 100 meters or more, however far you want to go, of a production line. So that's one driver of why we end up with these platforms together. On the one hand, modularity, like the Arduino example. On the other hand, just physicality. We need sensors distributed, and they're not in the same place. Another driver of this kind of multi-platform inevitability is the fact that peripherals like radios or an accelerometer become increasingly complex over time and more capable. But that means that if you buy a radio today, there are almost no radios you can buy for your embedded board that are just a radio. They are an embedded processor, which offers a serial API. They manage a radio on a packet-based network, sure. But sitting over here, we're going to have a separate computation block, or in this case, as we have a sensor, let's consider the accelerometer, to our main processor. This will have an independent clock. It will tick at a different rate than your processor here. So already we start to have quite the coordination issue between these things. Let's take a look inside the different blocks here. Here you can see we have, in this case, it's one physical interface with a couple of sensors on different platforms. Equally valid, there could be n physical interfaces from the same plant as well. In the first lecture that we go on to today, after the introduction, we'll focus on the computation block and how these processes look. In the subsequent lectures, we'll look at the memory, which isn't marked here but resides in the same block, and then ways of connecting these together in these fabrics. Here on the other side of the diagram, you'll notice that there is a kind of merge operator here. I think as it's a green block, this is not really a physical thing exactly, which drives an actuator. And the important part here is to consider that this actuator is fueled by multiple, potentially non-synchronous computation blocks and multiple sensors, which have to be brought together in some kind of sensible way to control this thing back here. Again, I think showing like the complexity of even a, kind of, what is that? 1, 2, 3, 4, 5, 6 block real-time system grows complex. How far can you go? What might you see in the book? This example I won't talk about in a ton of detail because the whole course is to explain many of these different acronyms you see here, like UART and I2C and so on and so forth. But if we think about something like a modern drone, this is a research example, but it's not particularly more complex, I would say, than a modern like quadricopter. You have a mainstream-ish processor, which is doing the control of the drone. You have a secondary ARM-based core, which is taking care of things like the sensors here, the GPS, IMU, and so on. And then finally, this is connected to some other sensors via an even more embedded processor. In actual fact, these two boards integrate. This is the Gumsticks platform right here. The specifics on the slide are not super important, but it's just to say like there's a progression here. And even if the first example, which I think is already rather complex from your point of view, entering embedded systems typically in this course, it can grow to become tremendously complex. And what you need here is supporting semantic notions that let you coordinate all this. Block certain things on, block one thing on another using a semaphore. Bring things into sync somehow, and these sorts of concerns. So that brings me to the end of the introduction. What we'll do with the rest of the time today is we'll move on to the computation lecture. But before I do, are there any questions, again, on the scope?
It's the second time you mentioned semaphore.
Yeah.
Exactly do you mean with that?
So a semaphore is a notion in embedded systems which comes from, originally, I think, trains. And a semaphore was like a flag to say whether you could stop or not. And if you can see the flag, you can go. But if you can't, then you must stop. So when we have parallelized kind of schedules, semaphores become really useful just exactly like that, as a way to flag that something can now begin or must end. So the one element of what we'll study when we get to the real-time scheduling part of the course. But it'll be a while. So now we're going to take a detour through some hardware first and then low-level software. But we'll come back to that about halfway through. Other questions? All right. Do we want to take a quick 5-minute break or just plow right on? Too much shrugging, no break. Got to be quick. So you'll notice online that the lectures are broken down into just 30-minute blocks. Typically, we'll get 2 of those 30 minutes in the physical lecture. It was just easier for me to make 30-minute videos, and it's probably a bit easier for you to watch them if you have a schedule with, little gaps in it. So let's talk about processors. Processors are obviously, hopefully you know this by now, the brain of your computer. They are the tiny block, typically inside the very large case, even if it's a laptop, that's doing all the work, or all the non-graphical, non-I/O work to make your software run. Almost every processor which we use today although Mac's going to change back again, I think, to some non-Intel architecture, is based on the x86 instruction set architecture. An instruction set architecture is basically the lowest level of language at which we interface with these processors. Well, the lowest level of language with which programmers interface with these systems, it's more correct to say. There's no particular reason, except historic accident, that the x86 architecture, which you'll have in every non-Mac machine I see here, unless there's a tablet that's kicking around someone's using, it's just due to market forces and where different companies were at different times in the 1980s. What every ISA gives us are the syntax and semantics of the instructions that the CPU is going to execute, and also how those instructions are stored. For example, how big are your instructions? On the standard Arduino, and I think the one you're using too, I think it's an 8-bit architecture, we have 8-bit instructions, which operate on 1 byte of memory at a time at the lowest level. By the time you get to the top of the Arduino IDE, you don't have to worry about that. You don't have to worry about converting everything into bytes. But if you're actually configuring any registers and so on the Arduino manually, and eventually you will have to do that, then you will see that they're all going to be 8 bits wide, with the exception of this weird storage register, which is not worth mentioning for now. We can implement different ISAs on different processor families, of course. So the x86 architecture has a number of variants. It's implemented on embedded processors like the Geode, all the way up to the latest and greatest Intel and AMD monsters. Code compiled for the same version of an ISA should interoperate. But here it gets a little bit sticky in embedded systems for the reasons that we just saw. So you can compile 8-bit AVR code for any 8-bit AVR. But as you just saw, on these processors, we tend to include a ton of peripherals. So the chance that your code is going to work on a different AVR if you're using the serial port, the I2C bus, maybe even different areas of memory, is not 100%. So in theory, this gives us a layer of compatibility, but you shouldn't think like the JVM or something like this, where it's going to work on every machine the same. If we consider the regular mainstream CPUs that we have, how do they look? Well, here you can see a generalized diagram of a CPU over there on the right-hand side. So the CPU has a control unit, which is provided with instructions which are taken from main memory. And based upon that, it runs the processor here. The processor combines a number of registers which hold the data to be immediately operated upon. So as you know from general programming, you have like your long-term storage, your hard disk, SSD, whatever. You have your RAM, which is where you store the stuff your program is working on. But at the lowest level, when the processor is going to operate on something, it gets moved into the registers. And this is the only place that the processor can apply its logic to. You'll have cache and stuff as well, of course, but that's just a level above this. And eventually, when you're actually doing the work, it's happening in those registers. Eventually, when the output is ready, it's provided to the system. Note what you don't see here. So on a mainstream processor, we don't see a lot of specialized blocks, and we don't see a lot of I/O. Go ahead.
You mentioned RAM, so the registers are still something different from RAM.
Yes, although, so our processors, our embedded processors, which I'll come to more in the next lecture, provide us with like an abstract notion of RAM, which is addressed. And in the case of most architectures, it's nice to make this the same. So actually, it's quite common for your registers, for you semantically, to be just a certain area of that memory, addressed in just the same way. Perhaps the low areas of the memory is normal. But they can actually be very different. Your RAM is often implemented in a separate block on the processor. It has different performance characteristics than your registers do. Or in larger embedded systems, you may even include your own RAM. So you may have DMA and you may attach a RAM chip. So the processor cannot operate directly on any of that data. It has to first be brought into the processor itself and onto the registers. I would say, generally speaking, processor designs are getting more, what's the word, simpler and more homogeneous if you look at the newest kind of embedded processors compared to things like the AVR, which has quite a rigid kind of memory allocation. But we will look at that in detail next lecture. What to say? What did I think I was saying about this? So basically, the x86 instruction set is the one from the original IBM PC. There was a cheaper knockoff variant called the Intel 8088. Those numbers are not particularly important, but it gained a lot of traction as in the early 1980s and basically became dominant. So you still find it today, but increasingly, actually, what happens with the x86 instruction set is that it's translated to different underlying instruction sets. So most processors do not natively interpret this anymore. They don't actually work with this. They have basically a layer which converts x86 into whatever the processor really runs. So all those tedious 1990s discussions about CISC, complex instruction set architectures like x86, versus RISC architectures like you get on your phone on ARM processors, are more or less null and void for mainstream machines. Everything is really ARM under the hood, but it can read x86, so no one cares much anymore. Our MCUs make a complete break with that. They don't care about, kind of mainstream anything. Everything is optimized again for, lowest price point, most efficiency. So the main way that we minimize costs is minimizing chip count. That means we integrate more and more, as much as you can, often a radio even, onto your core processor. This also minimizes size. So if you're interested in the lowest level hardware geeky stuff, then it's very interesting to look at how big some of the smallest packages are. You can, I think like 1.2 mil squares on a side is about where it's at for a 32-bit ARM Cortex M0, which is more powerful than the processor that you will use in this assignment. So we can make once you get to pure silicon, you can make these things almost arbitrarily tiny. And in fact, fun thing about Moore's law, we remember this probably from other courses, it means that every couple of years our PCs double in speed. Here it can work the opposite way too. If we fix the speed, every couple of years we can make that same processor half as big, if it's pure silicon. There are a number of complications, though, because, for example, your antenna is a certain size, your battery is a certain size, etc. Energy can be minimized in much the same way. I would say that low-power software engineering remains as much an art as a science, but the more integrated everything is, the better. So the less integrated a system is, the more that you're going to have to actively probe things to see if something has happened, for example. You can't wake up because a nice interrupt fired on your chip to tell you a result is ready if it's not integrated, these kinds of things. So generally, integration makes our energy management easier. But obviously, these things end up more and more specialized. Let's take a look at some specific components. What's on our MCU? Obviously, it has a compute core, just like the CPU does. It also has a certain number of general purpose registers that you can work with directly in assembler. In addition, it will have special registers. So for example, a well-known register will hold the state of peripherals. Are they turned on or are they turned off? Another well-known register will be holding results from the serial port when data arrives, and so on and so forth. So this is how all the libraries work at the lowest level, interrupts and registers. And if you know where the right registers are, and you get an interrupt that your serial port has data, you can just go look and get it. You don't have to start at that level, but again, I think it can be interesting in the later parts of the course to go a little bit deeper and see how this stuff works. Not only will we have RAM on our embedded processors, but also non-volatile memory. Here it's clearly going to be flash. It has to be silicon, otherwise it can't be integrated onto those chips. There are all different kinds of flash. We'll get to that next week. They have different trade-offs in the power consumption, the performance when reading, the performance when writing, and these sorts of things. You'll also get in-circuit programming and debugging support. So because the memory is on the processor needs some way to receive a program and execute it. There's a whole bunch of standards for this. I'm not going to get into them now. More and more, these tend to be wrapped up in nice, easy-to-use serial bootloaders. So you can plug the thing into your PC and just flash it. But if you're working with a more embedded device where you don't want to spend the space on those chips and connectors, it's quite common to see standards like JTAG, UDPI, I've forgotten the new Atmel standard, but there's a whole family of them. It's really annoying. You need like many different programmers in the lab. You'll also have timers. Timers are really interesting for a real-time systems course. You cannot put an accurate timer in pure silicon. So one of the components that's kind of annoying and we often end up embedding is a crystal oscillator. However, you can put pretty accurate like RC and PLL loops on your processor that will give you a clock signal that might be a bit less accurate. So that gets interesting already. You might be designing a board in the future or getting a hardware engineer to do that for you. You need to think about how accurate your clock should be. What can be done in silicon on this chip versus whether or not you need an external clock there. In addition to just running the processor, so reading instructions and executing them, that's the core processor speed, you'll have all kinds of derivative timers where you divide down those clock ticks and you have, for example, wake-up timers or watchdog timers in case your code goes wrong. And different processors will have a different number of these. Another important thing that's always there somewhere is analog to digital conversion. So on the one hand, we can talk to a sensor over a serial bus, right? That's one way to interact with the world. Oops. But how does that sensor interact with the world itself? In the end, everything is typically either voltage or current changes based on different kinds of sensing elements. That gets reduced to looking at and measuring voltages or generating voltages using an ADC, analog to digital converter, or a DAC, digital to analog converter. Finally, we end up with a whole range of embedded communication standards, increasingly actual radios, so a Bluetooth radio on chip, or even a Wi-Fi radio on chip, but in addition, a bunch of embedded standards. And we're going to study those in a special lecture, but things like I2C, SPI, UART, these kinds of things. So all this monolithic integration earns us quite some power improvements. Typically, modern processors will offer deep sleep modes, which range in power from a few microamps to, let's say, 100 nanoamps or so. That's an insanely small amount of power. And as a small kind of look ahead to the power management lecture, deep sleep mode is where it's at. You can play with the speed of a processor all day long in its active mode. And the faster you run it, the more power it consumes, which is intuitive. But that's almost never a way to win, because if you get your job done quicker and go back to your deep sleep mode, then you can reach these insanely low power numbers. So the job of low power design in real-time and embedded systems really becomes one of staying asleep as long as possible, waking up for as short a period as possible, and getting the job done. It almost doesn't matter if your code is good, how fast the processor runs while it's awake. In fact, faster may well be better. At this point, in the lab, but also even in commercial products, these processors can, for many useful tasks, although you have to look at the task, reach the shelf life of a commercial battery. Go ahead.
Is there no overhead from getting into sleep or out of sleep mode?
That's a good question. So just in case anybody at the back can't hear, it was, is there any overhead in entering or leaving sleep mode? There absolutely is. I think most processors don't, there's no real power blip for most processors that I can think of if you're going into sleep mode, say. But you spend time in active mode to shut down and then to wake up. So for that reason, not only is it good to spend as much time as you possibly can in sleep mode, it's also good to put your jobs together in time, as much as you can. But it's important to note that that's kind of the enemy of responsiveness. So then it gets complicated because our embedded processor, even though it's slower, is much faster than human perception, obviously. So with clever code, we can have something like let's say a fitness tracker, and it can always seem like it's on to you. It responds immediately whenever you touch it. But in reality, it's off 99.999% of the time. And until you change the angle of your wrist, you hit a button, it's not going to wake up and do anything. So there's a responsiveness versus power trade-off always. It's good to put wake-ups together, for sure. But the main thing is always getting back to sleep mode. To show you how far this goes, in reality, you can get power savings from sleeping in between requests and replies on many embedded buses. So this is super advanced, and probably you won't do it in your assignment, but when you have squoze every other little bit of power out of the thing, then what you should be doing is, when you communicate with your sensors, you start communication, go to sleep. You wake up when the communication is ready, process it, and then go back to sleep again. It's an effort trade-off too, of course, because every time you have like sleep-wake functionality, you have a place where you can mess up and you don't wake up again or whatever. So you have to also treat it a bit pragmatically. And you should eliminate the large, easy chunks of wake time and then, kind of go for the smaller and smaller fish as you can. It's one of the trickier bits of the things you'll code, because the problem is that you don't get any signal and you have no processing while you're asleep. So you can see it goes wrong often when you start playing with low power sleep modes, but that's all you're going to see because the processor's not on. Historically, the instruction sets for embedded systems are way more varied than CPUs. The Motorola 6800 series was super popular. That's like you used to see in old, very, very old Apples, the Apple I and Apple II. Zilog Z80s, as in the Sinclair Spectrum, Intel 8051s. These things are really sticky, because what will happen is somebody will build, for example, a helicopter control system for a helicopter that might have been designed in the 1970s, but is still in service somewhere in the world, and they use an 8051. So, kind of these instruction sets just get stuck in there in super expensive things in the world and end up being manufactured for the next 40 or 50 years. You can still buy these today. Nobody likes them. No one would ever use one in a new design, but they'll be with us for years to come. I would say, most of what you learn in this course, these things won't matter to you. The principles all do apply to these processes. They're just not going to be as good or be more painful. The kind of modern instruction sets here include things like the AVR instruction set. That's the instruction set of the ATmega chips, the ATtiny chips, the things that run Arduino code. PIC processors were the dominant kind of small industrial project or hobbyist processor before Arduino became like the one and only. It's just really an analog to the AVR instruction set, nothing too special to say there. MIPS you'll find in a ton of your routers, for example. Again, a good example of how things are sticky. There's no real reason to choose a MIPS architecture over an ARM one, but a lot of people started building routers that way, and so we still do. If you were selecting for a new design today, almost everything now has converged to the ARM thumb instruction set and the family of processors which are labeled M. So they start at M0, and there's a whole coding scheme. The M0s have no memory protection and no accelerators, and it goes all the way up to like an M7, which can run a low-end phone if one was so inclined. And these are really largely dominant. Why don't we take one for your assignment? It doesn't really matter, honestly. I mean, we have limited very low-level chip access, and we have a bunch of these already. If we're doing this assignment in 5 years, there's no doubt it'll be some flavor of ARM Cortex processor. A lot of this might seem like, what's the word? Ephemera from a software point of view. And it isn't really that you need to remember what the Zilog Z80 is for the purposes of this course or in your future career. It's just to say that it's kind of a zoo out there. There are many of these things, but all of the techniques that we're using, and for example, things like FreeRTOS, apply across all of them, in fact. Even horrible old 8051s can run FreeRTOS. So as these processors gather more multimedia features, not multimedia like video and audio necessarily, we tend to separate them out into something called digital signal processors. For me, this line has got awfully fuzzy over the last few years. It used to be, you had your 8-bit micros or 16-bit micros like the MSP430, whatever. And then if you wanted to do something with sound, for example, you would inevitably need large accumulators on the processor for doing calculations with bigger data. You might need a floating point unit, and you might need an FFT built in. Those are the kind of things we expect to see on DSPs. However, the higher-end Cortexes embed all of those things, and we don't always call them DSPs. So this is kind of a class that I think is being folded into the general microcontroller class. There's no absolute line there. I guess the only thing I didn't say there is where you would find them. You'll find DSP-like functionality or DSPs typically on things that deal with high-frequency signals. Not exclusively, but that's a great example. So if you have some cheap Bluetooth audio doohickey, that probably has a DSP. If you are doing, let me think about this. Yeah, image analysis, that's a great one. Then you still do have quite dedicated DSPs to efficiently handle, let's say, a parallel camera interface and to attach that to an application microprocessor. I don't think anyone's going to fuss too much about whether it's a micro or a DSP in any future job interviews or anything like this, though. Graphical processing units also deserve like an honorable mention. So we're just going through the types of processor now. We have the CPU, the MCU, DSPs, and now GPUs. Don't these belong running your computer games on your desktop with a giant fan attached to them? Yes, that is their natural place, but AI researchers have found all kinds of clever ways to reuse these for classification. Now, it's still a relatively new area, but we now have more and more embedded GPUs being produced that are easy to integrate with the kinds of processors we just talked about, the microcontroller units with sensors running real-time OSs. It's very hard to see these as low-power devices in any way, but remember what I already said about low power. It's all about sleep modes, right? So there's a small niche of kind of AI applications where if you have sporadic analysis, where you don't need to do it all the time, but when something happens, then potentially we could even have battery-powered GPUs. Or they're just applied with cameras, for example, to check things like soldering joints, which is still a real-time and embedded system, but just has no power constraints associated with it. Maybe a little sidebar there as well. So like, if you had power, why wouldn't you use a normal PC? Because you have a whole course here on embedded systems, which means it's complex, right? Well, actually, once you know how to build these things, many things will get more reliable. So if you've ever tried to have, let's say, some weird Linux box, like a weird Linux network repeater that runs, outside somewhere or something like this, you will very quickly be plagued by the complexity of that mainstream stack. All the little things that can go wrong across millions of lines of code that are not just designed for your app. So even when we don't need to do low power, and even when we have like plentiful resources potentially, we still often end up building dedicated embedded machines because we can absolutely we can test them in a bulletproof way. We can control every piece of functionality on them and how everything operates, which is possible on a mainstream device, but much more difficult. Another thing that's worth mentioning here are field programmable gate arrays. Again, this is something that is rather niche in the embedded space. You might find them in things like cleverly engineered oscilloscopes, which you can buy very cheaply, like little USB scopes. And the main reason that we don't see more FPGAs is that they lose their state typically once they're depowered. So what is an FPGA? I should probably started with that. It's a software definable CPU. So it's a fabric composed of gates onto which you can put an arbitrary processor architecture, which sounds super cool, and it is super cool. The problem with that reconfigurability is, with a normal FPGA, if you shut off the power, not only does your program go away, but your CPU goes away. It returns to being a fabric of gates again, of course. There are, though, increasingly flash FPGAs available, which don't lose their state when they're depowered, and also a much lower power to run. Because, of course, as we'll see in the memory lecture, if you need to keep a lot of memory state, that uses power all the time, not just when it's running. So a traditional FPGA, a RAM-based FPGA, cannot have a sleep mode as such, because if it stops being clocked, it's gone. A flash FPGA, you can put a processor image on, and it will last until the flash degrades, hundreds of years or whatever. So why do we use them at all? Well, it's basically kind of an intermediate between a real hardware ASIC, an application-specific integrated circuit, and software. So we can specify those soft cores using things like VHDL. Very complicated and fiddly compared to mainstream programming, but still it's a program. It can be changed over time to just what you need. It's very hard to give specific speedups when moving to like an FPGA architecture. I think the rough rule of thumb most people use is, if you can build a dedicated FPGA processor, you might be able to look at a 10x speedup on your software at the same clock speed. But that can vary wildly because there's big architectural differences between the two. More parallelizable software might be 100x faster on an FPGA. And software which can't be parallelized, well, might not be faster at all. It's entirely possible. The same kind of speedup exists if you move from an FPGA to a real custom processor. So you can kind of view this, I think, in many design exercises as kind of a trajectory. If you made 1 billion of your integrated hardware-software device, it should always really end up on its own ASIC. It's very rare that you should build it from separate components. And it's not uncommon for people to follow a trajectory which goes from pure software on commodity modules, jump wire on the desk, to a real board, but the same components, then to an FPGA implementation that shows how speedup can operate, and finally, you can go across the street and pay them 100,000 euros to make a real processor for you. But of course, the upfront costs of the processor are huge, so this tends to come later. I mentioned the difference between RAM and flash-based FPGAs. These are very interesting for our research group, actually, because they do have decent low-power sleep modes, and it means that we can build weird or exotic processors and really run them on a battery, which is what my little team cares a lot about. When it comes to reconfiguring FPGAs, there's monolithic reconfiguration. By far the most common, you just replace everything, but you can do modular. So for example, one of my students was working on a flash FPGA architecture that would let you dynamically deploy security cores whenever you needed to. So that's it for the processor overview. In this course, the most important thing is that you'll get to grips with microcontrollers and understand how those are different than CPUs. Although I think that the DSPs and FPGAs are rather interesting. There's stuff here we didn't mention as well. The ASICs just mean you had a real chip designer do it for you. Complex programmable logic devices still exist, but are rather obsolete at this point. They are the predecessor to FPGAs. Whereas an FPGA can be reprogrammed over and over, a CPLD, excuse me, a CPLD can only be programmed one time, and that's it. You've flashed an image onto it. They're also typically a lot smaller than FPGAs, so you can use them for things like simple Boolean logic attached to a couple of sentences or something like this. And programmable logic controllers are much the same. These are really like the descendants of conventional microcontrollers, typically used to control industrial systems before we had nice microcontroller standards that would plug into everything. A trend that you'll see a lot in industry today is them taking the old school PLCs, That's what the programmable logic controller stands for. And moving them on to microcontrollers. There are even whole virtualization schemes which let you take your ladder logic program, if that's what you're working with today, and move it to a conventional micro. So you can stop using these big clunky old things and move to something more recent. And that's it. That brings us to the end for the compute lecture. This is covered in the Lee and Sesha book in Chapter 1, the introduction, sections 1.1 and 1.2 only, and Chapter 8 on embedded processors, which we've covered more or less all of. We're a little bit thinner on the FPGAs and the DSPs than the book is, but that's just because we focus on the micros. So, excuse me, any questions on the processor section? No, everybody needs a coffee. I think that is very reasonable. Then we'll leave it there. Next week, we look at, let me just check my schedule. Oops, that's a different lecture. Next week, we will look at memory and embedded programming. If you have any questions in the meantime, feel free to drop me an email. I'll try and get back to you quickly. It's just one lecture per week. This is the slot. And then the labs are in the same slot. So we do this 3 times over. Then you get your 2 labs. Then another 2 lectures. And then it's all lab and assignment time.